Hi, my name is Shihab. This project was something I completed for my honors degree in statistics from HSTU, driven by my curiosity. Now, I'm going to present image recognition using artificial neural networks, or ANNs. Transforming pixels into knowledge is my mission. Here are the working objectives. Let's move to the first objective, Introduction to Image Recognition. What exactly is image recognition? It's the process of identifying an object or feature in an image or video. In these two pictures, we see many objects, each identified with AI. Now, how do I prepare data for use? I use the MNIST dataset from TensorFlow, a collection of 70,000 samples. It contains 10 classes from 0 to 9. Before using the dataset, I pre-process it through normalization and reshaping. Here we see how the MNIST dataset looks with its labels. We use 80% of the total dataset for training and the rest for testing. Here is the distribution of the dataset that I used. From the data, I take a sample as shown on the screen. The picture dimensions are 28 by 28 pixels, totaling 784 pixels. Each pixel has a value based on its brightness or darkness, with the brightest pixels representing the highest values and the darkest ones representing the lowest. Here is the pixel representation of the image. Okay, now if we convert the image to an array, it'll look like this. Since ANNs work in one dimension, but our input data is in two dimensions, we need to convert the image. These values serve as inputs for the ANN model. So, what is an artificial neural network? It mimics the way nerve cells work in the human brain. The model has one input layer, one hidden layer, and one output layer. In the hidden layer, I use 128 neurons with the activation function RealU. For the output layer, I use softmax as the activation function. The model summary shows a function called flatten, used to transform two-dimensional data into one dimension. The total number of parameters is 101,770. Now here, the model works as shown in the animation, and where you can see how it predicts an image of the digit 9 as 9. This step-by-step prediction showcases the power of neural networks in recognizing images accurately. It's fascinating to see how the model processes the image and translates it into the correct label. After training, I evaluate the model. Using a test sample, I check the model's accuracy in recognizing digits. The model achieved 97.9% accuracy. I tested multiple times, and the model mostly predicted correctly, though it sometimes misclassified images. For example, in the third picture, it misclassified a 3 as a 2. So the model has a 2.1% error rate. Now the question is, how can we analyze this error? The answer is using a confusion matrix. The confusion matrix summarizes the predictions in matrix form. In the fourth column, it correctly classified 3 as 3, 957 times out of 1,028, but misclassified 71 times, predicting 2 or 5 as 3, 22 times. If you have any confusion about the confusion matrix, you can watch the scatter plot for better understanding. In here, you can see that I used 25 epochs, and the graph shows a decreasing trend in training loss and an increase in training accuracy. This indicates a good model, but there's a catch. When we validate, we see a different picture. Here we see that validation accuracy decreases and validation loss increases after a few epochs, indicating overfitting. From this, we conclude that 5 epochs are enough for training the model. I used 5 epochs for both ANN and convolutional neural network CNN on the same dataset. Here we can see that CNN outperforms AN, where ANN after 5 epochs achieves 97.9% training accuracy, and CNN achieves 99.5%. I trained the CNN model with the same dataset, and you can see the status of training and validation after 25 epochs in the graph. As the graph shows, the training accuracy continues to increase while the validation accuracy fluctuates slightly. This suggests the model is still learning and generalizing well, but we need to be mindful of potential overfitting as the epochs increase. Now we can clearly see the difference between these two models. AN use fully connected layers and treat each pixel as a separate feature, making them better suited for simpler data sets and tasks. However, they have more parameters, which increases the risk of overfitting. CNN, on the other hand, use convolutional and pooling layers that capture the spatial structure of images, allowing them to learn hierarchical features and excel in image recognition. They also have fewer parameters, making them less prone to overfitting. In short, CNN are the better choice for complex datasets like to their performance in image recognition tasks. I created a digit identifier app that can instantly recognize digits in images using my ANN model. In my next video, I'll demonstrate how it works in real time and show you how the app recognizes digits instantly. Neural networks are transforming the world in ways we see every day. In handwritten digit recognition, they can identify numbers like in the MNIST dataset. They're used in object recognition, detecting and classifying items in images. In healthcare, they assist with diagnosing diseases through medical scans. Facial recognition technology helps in security and identity verification. Neural networks also enable machines to understand natural scenes, analyze documents, and improve industrial automation. Even in art, they help identify styles and detect forgeries. If you have any questions, feel free to leave a comment. If you would like more information about my project, please feel free to reach out to me via email or connect with me on LinkedIn. Thank you for taking the time to watch my video and listen to my presentation. I appreciate your interest, and I hope you found this insightful. Have a great day.